Hello. Welcome to this live interaction session of week 8. We'll start in a couple of minutes. Good evening. Okay, good evening, everyone. So let's start. Um, Okay, so in the last session, we had seen an introduction to geographic information system, and we had looked at different components of a GIS system like hardware, software, different data types like raster and vector, right? So today, yes, okay. So today we'll try to look at these different data types in a QGIS environment. So I'll show different raster types and vector types so that we can have a better idea of how such data looks like. And then we will look at some spatial data analysis methods like interpolation, and then we'll look at different types of map projections and solve a couple of questions from previous year's assignments. So let's start. A geographic information system stores a spatial information about a real world as a collection of thematic layers, and these layers are linked together with associated geography. And this geographically referenced data, it describes both location and characteristics of spatial features on earth's surface. So in the last session also we saw that there are two different data types, raster and a vector. So raster is a data type which represents spatial information by dividing it into regularly spaced and quantized cells. Right. So here on the left figure we see this raster data. Uh, right. So these small boxes, they are called cells. Right. And this each cell has an x coordinate and y coordinate associated with it, and it also has a uh, DN number or some other information associated with it. It could be like elevation or groundwater value, rainfall value, anything. So these cells will have location information and one more attribute information. So yeah, each pixel location can be represented as number of rows and columns. So like this pixel can be represented as if this is the origin, then this would be like 1 1. Then next pixel would be 1 2, and along the row we will have 2 1 and so on. And yeah, there is a cell value to represent attribute or property of interest, as we talked. And the second data type is vector. So in a vector the data is stored as a collection of points or lines or polygons, and points like points represent discrete points on Earth's surface. Lines, they represent linear features like rivers or roads, and polygons, they represent bounded areas, like um, political boundaries or lakes or other such things. So we'll go to QGIS interface now, and we'll see each of these data types in a QGIS environment. I hope the screen is visible.
Yes, ma'am.
Okay. Um, so let's add layers. Mm. So first we will look at vector layers. So here in layer, I can go to add layer, add vector layer, and then here I can search the uh, source folder. So in vectors, we have points, lines, and polygons, right? So let's look at point layer first. So I have added this point layer. Now here, if I move my cursor over any of the points, here in the coordinate window, I can see the coordinate of that particular point. And uh, here, this is the projection system for this data set. So this yellow point, it has been selected in this vector file, right? So here I can open the attribute table, and I can see this is my selected point. So these are the associated latitudes and longitudes, and this is the station code, and this is the attribute value uh, corresponding to that particular point. So this data set, it's a groundwater data set. So each of these points represent wells, and the data set is corresponding groundwater level value. So if you want to look at this with respect to a map in the background, then we can add. There are different types of maps which can be added. Here I'm going to add a Google satellite map. So let's change this color. Right. So if I zoom out, uh, yeah, I'll be able to see the location of these points. So here I can select all the points, or I can deselect, I can select a couple of points and then perform different operations on a subset of points from this data set, or all the points, or anything according to my requirement. Right, so we saw the attribute table with lat long and other information. So this is one type of a point layer. So it was like collection of a point data. So I have one more point layer to show. So I can either add layer from this tab, or I can directly drag and drop the layer which I want to add. So here the layers can be turned on and off in this layers panel. So here now currently both the point layers are on, and this map layer is also on. So I can uh, like turn off one of the layers, or I can switch it on if I want to observe both the layers together. So here, this is the data set of all the dams around the globe, right? So this is a point layer with so many data points. So this is some 35,000 data points, I think. Right. So if we concentrate over India, there are these many dams in our country. Let's look at the attribute table associated with this. So there are different ID values. There is latitude, longitude information. Then yeah, there is some station code and other things. Right. So this was point layers, and then we will see uh, lines. So here in the layer styling panel, I can change the width of these lines, or I can change the opacity. These here, the attribute table. Okay, it looks like this. I can represent it with different colors. So currently I'm going with blue. So these are all the line features, line data type. So these paths are they coincide with all the rivers. Uh, this is Ganga, Yamuna, then there is Kosi, Gandak. Right. So uh, in a small scale map, we can represent these rivers as a linear feature. Right. Next we have polygons. So this is a collection of different bounded areas. So each bounded area represents each state. So here, if I select this, then I'll be selecting Madhya Pradesh. Then here I'll be selecting Maharashtra, and so on. Right. So in the shapefile, in the attribute table, I have a state name corresponding to each polygon. So here, if I select Andaman and Nicobar in the attribute table, then here in the map also it will get selected. If I select Kerala, it will get selected in the map, and so on. And now, if I want to look at these point features on top of the India map, so I just have to bring these features to the top. So here now, India state boundary map is at the bottom. Then on top of that, I can open the groundwater layer data. Uh, is it updated? Huh. Right. So on top of this, I can open another point layer on top of this, I can open another point layer. Then I can also open the reverse, the line layer. So here, yeah, so these different vector data types can be viewed as a can be viewed separately, or it can be viewed together as a collection of different layers. So GIS enables us to do that. Now we'll look at raster data type. So let's switch off all these layers. Uh, Right. So this is a digital elevation model of the Ganga Brahmaputra basin. So all these values, there, each of this point will be a collection of rows and columns. So there will be multiple cells, each cell containing a location information and an elevation information, because this is a digital elevation model. So let's change the color scheme. uh, I want it to be single band pseudo color. Okay, this is a good color palette, but uh, okay. So after making it 5,000, I am able to see the variations in the topography in a much better way, right? So here, if we zoom in, are you able to look at these small boxes here? Okay. Yeah, so here these are small cells of same size, right? So these cells, they are the smallest unit of this raster, and then each cell will contain a unique elevation information. So here I have this identify features tool. So if I collect on each cell, it will give me uh, elevation value corresponding to that cell. So I think we'll be able to look at the contrast better maybe here. Right. Now if I make the maximum value up to 1,000, then I'll be able to see the differences in elevation better for low elevation regions. So here, yeah. So here we can see the cells much clearly, right? So the size of each cell will be 30 meter by 30 meter. And here also, here now we have slightly lower elevation values. So these values will be elevation values above the reference datum. So this is 462 meters above the datum, and then each cell will have a corresponding coordinate value also, which can be seen from here. All right, so these were the data types, raster and vector. In vector, we saw lines, points, and polygons. And we can combine raster layers and vector layers together as well. So this is my raster layer which is currently open. So I can look at this reverse layer on top of the raster layer. So here now I'll have, um, if I'm looking at both the layers together, then it will give me an edge during the analysis. So I can um, have a better idea of how the river is going to flow, and then I can um, evaluate evaluate it based on the DEM which is there in the background. Okay, so we'll go back to the presentation.
Ma'am, from where we can get the DEM file?
So there are different sites from where you can download the digital elevation model. So the one that I showed is from Allos DEM. You can also download SRTM DMs or Tandemx. So there are these different types of digital elevation models which are freely available. So I think there is a USGS website from where you can get SRTM data, and you can Google it. You'll find it there. If or I'll do one thing, when I'm uploading the presentation, I'll add the links to these sites.
Okay, ma'am.
Okay, so next we have triangulated irregular network or TIN. So a TIN is a vector representation of continuous spatial data. So this model uses contiguous non-overlapping triangles to represent a three-dimensional surface. So each point will have length, width, and height like information. The elevation value of a specific point on the Earth's surface is modeled as the vertex of a triangle. So here, this each vertex will have a specific elevation value, um, and yeah, and then these triangles are, so these triangles, each of them, they have roughly similar slopes. Yeah, these irregular triangles represent areas of similar slope, and these are based on Delaunay triangulation. So we'll look at that. So here, this figure shows how these points are constructed, right? So here we have three different points, each having X, Y, and Z information, and then based on this, a small surface is generated which will have a similar slope, right? So here, this second figure, it shows how a tin model is generated over for a topographic surface. So these are generally used to show elevations. So here, when the slope value is changing very quickly, so in the areas of peaks, we will have slopes changing uh, more frequently than the low lying areas, right? So in such areas, the size of the triangle will be very small, and the triangles will be crowded because the slope values are changing more frequently. So here we have small triangles in this area of high topography, and then as we move to a low topographic area, the sizes of the triangles are also getting bigger. So this is this shows topographic representation of how a tin model will represent an elevated surface. So here, each of these triangles, they are shown, so they can show the digital elevation. So these are the triangular facets shaded by elevation and hill shading. And then we can see that it fairly represents the topography. Uh, yeah, about this Delaunay triangulation. So here for any, so these triangles are created using a certain set of rules, right? So here, uh, if you, the set of rule over here is such that if you circumscribe any circle passing through uh, three like three vertices of any triangle, then any other vertex, it should not fall within that circumscribed within that circle. So this is the um, rule which is followed when these models are created. Okay, so this is also a similar example. So here we can see that these high high topography area, they have uh, more density of these triangles, and then low lying areas they have lesser density. And here the model, it approximately displays the topography of this region. So the advantages of this in network is that it is ideal for irregularly shaped datasets. Yeah, fewer nodes can be used in the areas that don't change much. Fewer number of points are required to model this surface. Therefore, these files generally have a smaller file size as compared to digital elevation models, which have, if the cell size is very small, then the file size can get very huge. Right, the raster image that I showed, the digital elevation model, it has a very large file size, up to a few GBs or something. Yeah, and another advantage of this technique is that we can change the size of the triangle depending on the topography, as opposed to a raster format where we cannot change the cell size. The cell size is fixed. Next is topology. So topology, it expresses the spatial relationships between connecting or adjacent vector features. So these features can be points or polylines or polygons in the GIS. And topology or topology based data are useful for detecting and correcting digitizing errors. So we'll see that in next few slides. So this is a topology map of London Underground Network. So here, these uh, symbols, they show uh, some information about whether the trains can be changed at these stations or something like that. So using this map, we can, so this map is showing different relationships between different linear features. Like these linear features are also represented in different colors, right? So here, these are different paths. Then these linear features and these point features, they are put together to give some meaningful information. Uh, Yeah. Then we have topology errors. So topology errors, they are based on vector feature types. So you have different types of errors in polygons and polylines. So in polygons, we can have errors like unclosed polygons or gaps between polygon borders or overlapping polygon borders. So here, this is one of the examples where there is a gap between these two polygons. So we saw a state, saw a state map, right? So there, like two adjacent states, they should they should not have any overlap between them, or there shouldn't be any boundaries between them either. So there has to be these rules to be followed, otherwise there will be conflicts, right? So this state cannot have any territory in the other state, or there cannot be uh, an area which is not there in any of the states. So these topological rules are required to correct such errors. Next, we have polylines, where features do not meet perfectly at a point. Right. So there can be two different types of errors. Like undershoot is if a gap exists between the lines, and overshoot if the line ends beyond the line it should connect to. So here in one we can see an example of undershoot, right? So here this road is not connected to the main road properly. So here it just stops before getting connected to the other road. Or here it extends beyond the main road. So when we are using maps, like when we are using Google Maps and all, if they have such errors, then it might be difficult for us to navigate. So these errors need to be taken into account, and they need to be corrected. So we make a set of rules for such features, and we make sure that there are no such errors when we are making the maps. So undershoots occur when digitized vector lines that should connect to each other don't quite touch. And overshoot happens if the line ends beyond the line it should connect to. And slivers occur when the vertices of two polygons do not match up on their borders. Right. Okay. Next we have buffers. So these are all different types of spatial analysis on a vector dataset. So spatial analysis uses spatial information to extract new and additional meaning from the GIS data. So we saw these vector layers of points, lines, and polygons, right? So these are different operations that we can do on these data sets to obtain a different type of information from this data. So GIS applications normally have spatial analysis tools for feature statistics or geoprocessing, such as feature buffering. So buffering usually creates two areas. One area that is within a specified distance to selected real world features, and other which is beyond this distance. The area that is within the specified distance is called the buffer zone. So here, these buffer zones are represented for each point, line, and polygon data types. So here, around each points, we have a buffer zone of a certain radius. Here, along these river features, we have a buffer zone of certain length, right? And here, along these rectangular polygons, also we have a buffer. So in GIS application, buffer zones are always represented as vector polygons enclosing the other polygon, line, or point features. So this also we can perform this operation in QGIS and C. So uh, yeah, so this is our point data, right? Uh, so here we can go to vector geoprocessing tools. Uh, it's not getting up. Okay, it came. And buffer. So in input layer, I can add my uh, point layer. Here, distance will be radius along that point, and here the unit is in meter. So I suppose I want to make 100-meter radius around each point, and then other features I'll just keep as it is. So here I have a buffered layer, right? So this buffered layer has been generated. So I'll put my original point layer on top of this buffered layer, and then I can zoom in for each point to see. So here I can see that a buffer layer, okay, is it updated? Okay. So a buffer layer has been generated around each point. So I can go to other points also. Um, right here, around each point, I have a buffer layer. Now I can do the same operation for all the points, or I can only select some of the points in this layer and then again do the same operation. Right. So here previously what we just did the whole entire operation for all the points. So what if I want to do this operation for only these 3 points? So I will only select, so this is a select feature. So I will only select these 3 points and then again do the same operation buffer. Now here I have the option of doing selected features only, right? So selected features only, and I want to make a buffer of again 100 meters. Right, so now here I have uh, this buffer generated around only these selected points. Then we can do the same buffering for rivers also. So here, vector geoprocessing tools, buffer. So here we should see, be careful that the unit is in degrees. So um, I'll make this 0.1 degrees. So this buffer layer is generated along each river. So this is the width of the buffer layer. So we can do all these different types of analysis in a GIS environment. So if you want to check for polygons, uh, yeah, uh, yeah. So this is a data set of all the reservoirs in the globe. So I will just change the color. Right. So here I can do the same uh, buffer processing for the selected reservoirs. So if we zoom in, then we can see that this buffer layer has been generated properly. So this extra distance, right? So this is around 100 meters. So this 100-meter buffer has been generated from the boundary of this reservoir. So we can use this type of analysis in so there can be different applications of this. So for river, we can see like we can generate a swath along the river. So if there is a particular region along the river floodplain which is more susceptible to floods or something, then we can use this. We can generate buffers and easily delineate those regions. So this process can have different types of applications. So okay, we'll go back to our presentation. Uh, Then there is spatial overlay. This is also another type of spatial analysis. So this is a process that allows you to identify relationships between two polygon features that share all or part of the same area. The output vector layer is a combination of the input features information. So there are different types of spatial overlay. So there is intersection where the output layer contains all areas where both layers overlap. So this is intersection. Then there is union where the output layer contains all areas of the two input layers combined. So this is both the input layers combined. Then we have symmetrical difference where you have all the areas of the input layers except where the two layers overlap. So and then there is difference where the output layer contains all the areas of the first input layers that do not overlap with the second input layer. So this also we can check in GIS. Right. So I will just generate two random uh, vector files. So let me just create a temporary scratch layer. So let's call it P1. Right. Geometry type here is polygon. The projection system is same as the projection system in my QGIS environment. Um, I just create a field. Okay. So this is my first layer. Uh, so I'll keep it at the top and then I'll create another temporary layer. Let's call it P2. Okay. So so here in P1 I created one shape with a rectangle. Uh, and in P2 I'll make a circular shape. Add a circle and then save. So here in geoprocessing tools, I have all these different options to do clipping, dissolving, difference, intersection, symmetrical difference. Right. So first, what we saw intersection. So we will see intersection of P1 and P2. Input layer is P1, overlay layer is P2, and then I'll just generate a temporary layer. Okay, so here if I close this, I close the other layers, then this intersection layer has been generated. Okay, so this is the intersection layers, right? Intersection. Then we have union. Uh, for union, I can select P1 and P2 and run. Right, so this gives me a union of these two layers. I can do symmetrical difference between P1 and P2. Right, so here only the portion where P1 and P2 intersect is not there. Uh, and then last we have dissolve. No, okay, we had difference. Difference. So first layer is P1, second layer is P2. So it will generate a layer of P1 where P2 is not there. Right. So this is P1 without the P2 part. So this is how we can perform all the spatial overlay functions in GIS environment. Okay. So let's move to spatial interpolation. Right. So spatial interpolation is the process of using points with known values to estimate other points with unknown values. So so we saw this groundwater layer, groundwater point data set, right? So we had different groundwater points. So these are the wells. This is the data from groundwater wells. So it is not feasible to dig groundwater wells all over, right? So if this is an area, these wells can only be at certain places. So if we want to know the groundwater value in an unknown point, so there in that case we use spatial interpolation methods to use data from these known points, and then we can generate a function which passes through these known points, and we can estimate values of the function at an unknown point. So elevation data, precipitation, snow accumulation, water table, population density, these are some type of data that can be computed using interpolation. So, because of high cost and limited resources, data collection is usually conducted only in a limited number of selected point locations like these. And in GIS, spatial interpolation of these points can be applied to create a raster surface with estimates made for all the raster cells. So, this map here, it shows a temperature map interpolated from South African weather stations. So, here, these stations. Uh, these are the only points where this temperature data is recorded. So this the information from these points, it was interpolated within the region to predict the temperature values at unknown points inside the same region. Okay. Is the slide changing? Okay. So we have different types of interpolation techniques. So first there is global versus local interpolation. So global interpolation, it uses all the available known points in the study area to estimate the value of an unknown point located within the same study area. And local interpolation, it only uses a sample of known points to estimate the unknown value. So we had these groundwater points data, right? So in global interpolation, the value of all these points will be used to estimate the value at an unknown point. So if I want to estimate the value, suppose at this point. So for this point also, all these points will be included to predict that value. But in local interpolation, only points in the local neighborhood of the that particular unknown point will be used to predict its value. Next we have uh, deterministic versus stochastic interpolation. So in deterministic interpolation method, it is based on exactly predetermined spatial contexts, such as the extent of similarity or the degree of smoothing in the dataset. And this method provides no assessment of errors with the predicted values. Whereas in stochastic interpolation method, this method considers a random function, including spatial dependence between 2 points, and it quantifies the spatial autocorrelation among measured points and accounts for the spatial configuration of the sample points around the prediction location. So, kriging is an example of. So we will look at these methods in upcoming slides. So this interpolation method offers assessment of prediction errors with the estimated variances. So we'll look at these methods in the next slides. So these are some of the spatial interpolation models, right? So we have trend. First is trend surface model. So we'll look at some of these models. So trend surface model, it can be thought as a regression on spatial coordinates which are known to us, where these coefficients apply to those coordinate values and to the interplay of these coordinate values. So there can be different order models of this trend surface. So there is zeroth order trend surface model. So first and simplest model is the zeroth order model, which takes on the following expression: z is equal to a, where the intercept A is the mean precipitation value of all the sample points. So this first map, it shows an example of zeroth order trend surface. So here, all of these points, they have certain precipitation values associated with them. And then this entire surface, so if we pick any random point in this surface, so all of these random points will have same value. Z is equal to A, and A will be the mean value of all these points. So this is like very simple kind of interpolation. So most of the times this is not very accurate. Then there is first order trend surface. So this is a slanted flat plane whose formula is given by Z is equal to A plus Bx plus Cy, where X and Y are the coordinate pairs. So here, these for these different points, uh, this formula is used. So Z will be the if this is a precipitation data, so then Z will be the precipitation value associated with that particular point, and XY will be its coordinate values. And then based on, so we will have these many number of equations, right? For okay, these uh, some 21 points, right? So we will have 21 equations, and we have three unknowns. So using these equations, we can calculate the value of unknowns. Then we can just select any random point within the region, and then for this point we will have x and y values. Then we know, after solving the equations, we know values of a, b, and c, and then we can substitute these x and y into the same equation, and then we can find the value of z. So this is how, like, all these different interpolation models will work. Then we have, more the complexity of this equation. I mean, the interpolation can be made better and better using different techniques. So then we have second order trend surface, where the second order surface polynomial is a parabolic surface whose formula is given by this. So we can see, when we use different types of trend models, we get different results of spatial interpolation. So this is for a trend surface model. Then we'll look at the Thyssen polygon method. So this method, it assigns to all unsampled locations the value of the closest sampled location. So if I have a set of randomly distributed points, and suppose this is my uh, unknown point for which I want to find the value for this location. So here in this method, it will check which is the closest point with known value to this point, which is this point here. So this unknown point will get assigned the value of that particular point. So here, between every 2 points, this will be the midpoint which will be separating all the data from between these 2 points. Then here, between these 2 points, this midpoint will separate data from this point and this point. Then here we will have, this will be the midpoint, right? Here this will be the midpoint. So this is how different polygons will be generated in this Thyssen polygon method. So this generates a tessellated surface where lines that split the midpoint between each sampled location are connected, thus enclosing an area. And then each area ends up enclosing a sample point whose value it inherits. So here, these are different types of Thyssen polygons which are generated, right? So here, the point which is lying inside that polygon, so it might be any point, this point, this point, this point, this point. So all of these points will have one common value, which is uh, the value of a known point in that Thyssen polygon. So this is how the interpolated data will look like if we use this method. So here, the precipitation values, they are low in red color and high in blue color. This method is also called the nearest neighbor method, and surface values change abruptly across the tested boundaries, and which is not representative of most of the surface in nature. So this method is also not very accurate. So because here, if the precipitation value in this area is some 10 or 20, is between 10 to 20, then here suddenly, even if the point is very close to the previous point, suddenly the value will change across the boundary. So this is not a very true representation of most of the surfaces in, like, in nature. uh, Next, is the slide changing? Okay. Then there is IDW interpolation method, which is also known as the full form is inverse distance weighted. So in this technique, it computes an average value for unsampled locations using values from nearby weighted locations. So if this is my unknown location, and these are all the known locations around this point, right? So it will assign weights to each of these locations depending on what is the distance between these points. So here, this is the closest, right? Then this is slightly further, then this, then we have this, and then this is the farthest. So uh, it will assign weights which are inversely proportional to the distance between these points. So that is why it is inverse distance. So here, this point will have the highest weight. So the value of this point will depend more on value of this point, and then the weights, they sort of decrease as the distance between these points increases. So the weights are proportional to the proximity of the sampled points to the unsampled location. And this can be specified by the IDW power coefficient. So the larger the power coefficient, the stronger the weight of nearby points. So here, this is the power coefficient, right? So we said that the weight is inversely proportional to the distance, and then there is some power to this distance which we can change. So it can be proportional to 1 by d, or it can be proportional to 1 by d square, or it can be proportional to 1 by d cube, and so on. So higher the power of this d, more will be the weightage of nearest point. So for higher values of d, we'll have more and more weightage on the closer points and lesser weightage on the farther points. So we have these two images with different values of n. So this is the formula for estimating the value of z at an unsampled location j. So this is I is equal to 1 to n, and then zi will be the value at sample point, and dij is the distance between the unknown point and the sample point, and n is the power divided by summation of 1 by dij raised to n. The parameter n is the weight parameter which is applied as an exponent to the distance, thus amplifying the irrelevance of a point at location I as distance to j increases. So we just saw this, right? So here we have power coefficient of 2, and in this example we have power coefficient of 15. So the effect of nearby areas will be very high in this case, and it will be relatively less in first case. So this is how, if we change the value of n, the interpolation will be different in IDW. Next, we have Kriging interpolation method. So, Kriging is an interpolation method that makes predictions at unsampled locations using a linear combination of observations at nearby sampled locations. And then the influence of each observation on the Kriging prediction is based on several factors. So one of it is the geographical proximity to the unsampled locations, then the spatial arrangement of all these observations like data configurations, such as clustering of observations in oversampled areas. So it also takes into account the spatial correlations between the points nearby the unsampled locations and the pattern of spatial correlation of the data. So the advantages of this method are that it provides a measure of uncertainty attached to the results. So this is one of the, so this is what we saw in the stochastic methods, right? Is that it provides a measure of uncertainty. Uh, that is Kriging variance. This is the map of variance. So it also accounts for direction dependent relationships. So it takes into account different, I mean, it takes into account relationships between all these points also. Weights are assigned to observations based on the spatial correlation of the data instead of assumptions made by the analyst for IDW. Here in IDW, we assume that each point will have some sort of effect on the unsampled location, right? So even for the points further away, we have some sort of weight associated with it, uh, to have to which contributes to the value or at this unsampled location. But then in Kriging method, it takes into account the spatial correlations between these points. Here, the predictions are not constrained to the range of observations used for interpolation. So this is how the interpolated surface looks like in Kriging interpolation method. Uh, and this is the variance map. So here, the points which are shaded in a which have a lighter shade of red, they have the least variance associated with them, and so there will be and these darker points, they have the highest variance associated. So here we can see why these points will have higher variance, because see here there are no points available on this side of the region, right? So here the interpolated value of these areas, it will be only based on all the other points from this side itself. So here the values, interpolated values that we obtain at these points, they will not be so there will be higher amount of uncertainty associated with these interpolated values as compared to these values where you have all the nearby points with known values, right? So the interpolated value in these areas uh, will be having lesser uncertainty associated with it. Okay. Next, we have a spline method of interpolation. So here, spline estimates a value using mathematical function that minimizes the overall surface curvature, resulting in a smooth surface that passes exactly through the input points. So here, this interpolated surface, it will, it has to pass through all the input points, so all the sample points where the values are known, the interpolated surface will pass through all these points, and it will make sure that the overall curvature is the minimum for this surface, resulting in smooth surface that passes exactly through the input points. Conceptually, it is Uh, someone has raised a hand. Yes?
Sorry, ma'am, nothing, ma'am.
Okay. So conceptually, it is analogous to bending a sheet of rubber to pass through known points while minimizing the total curvature. It fits a mathematical function to a specified number of nearest input points while passing through the sample points. And this method is best for gently varying surfaces such as elevation or water table heights or pollution concentrations, etc. So we will solve. So based on this, we will solve some of the questions from previous year's assignments, and So I'll give you some time to respond to these questions, and then we'll discuss each of them. You can write your answers in the chat box. Right. Mukesh. Right, right. So, the trend surface model is a special interpolation technique which uses a polynomial equation to estimate the value of unknown points. So, this is true. So, we saw in the trend surface model, right? So, here all of these are polynomial equations to estimate the value of unknown surfaces. So this is true. Then data procurement in GIS involves remotely sensed image, scan of a hard copy map, manual digitization of a scanned map. So all of these methods can be used as a data procurement in GIS. So we can use like remotely sensed images which have uh, like remotely sensed images, they will have the geographical information associated with them. So these will be georeferenced images, or scan of a hard copy or digitization of a scanned map. So these data sets, they might not have like they might not be georeferenced when we open it in a digital platform. So these data sets, they need to be georeferenced first for analysis in GI. So georeferencing is like we can open like normal images without any geographic information associated with it also. So if there is like some map, so this is in uh, image format like JPG or PNG or anything. So this here, suppose this is a map of a certain region. So this map will not necessarily have geographical coordinates associated with each point. So we need to know coordinates of certain points in the map, and then we will georeference this map. So we will select each point, and then we will add coordinates to these points, and then based on the coordinates that we give as an input, it will generate so we need to give a coordinate system also, and then based on that, coordinates for all the other unknown points will be generated. So this is called georeferencing a map. So here we have all of these, and then which among these governs the relationship between various vector features in a map. So this is topology. We just saw this, right? You can try this. So here you can consider n is equal to 1. So I'll give you the formula again. So this is using IDW method, and the formula was zk is equal to summation I is equal to 1 to n. Let's call this p. Okay, and then zi divided by di to the power n 1 to p. So here p will be 3 number of points. 1 by di to the power n. So here we are considering n is equal to 1, and z is value of the known point. Zk is the value which we are going to estimate. So zk is the value at x, and yeah, I is total number of points. D is the estimated distance between the unknown point and known point. So this distance is also given, and value of z at each of these points is also given, and n is equal to 1. So you can try solving this. E- Mm. Is anyone else getting some other answer or the same answer? C. Mm. Okay, we'll try to solve this. So here, uh, zk is, so we have 3 points. So for first, for I is equal to 1, let's start with a b and c. So for the first point, zi is 77 and di is 7 and n is 1, so we don't have to worry about that. For second point, we have 72 by 9. And for third point, we have 90 by 10. And then here we'll have sum of 1 by 7 plus 1 by 9 plus 1 by 10. So this is the expansion of this formula for 3 points. And then here we get 11 plus 8 plus 9 divided by this is 0.353968. So this is the evaluation of these fractions. So we have so this is approximately 79.10. So this is the answer. I hope this is clear. So here you can play with the value of n, and you can check how the value at x differs uh, if we change the value of n. So for large, you can try for n is equal to 15. So here our current value is 79. So the influence of so this point is closest to point A, right? So the influence of A is higher on this point as compared to B and C. So if we increase the value of n, then the influence of A will be even higher. So you can see how the value at point X it changes for different values of n. Right. So these are the next couple of questions. Right. 16C. Yeah. So two vector layers. The answers are correct. 14. Okay. So two vector layers, namely forest types and soil types of the same geographic area are given. What is the spatial overlay function to be used for extracting a specific plant type growing in a particular soil? So suppose uh, so if you have two vector layers of forest types and soil types, then if we want to find the specific type of uh, plant growing in one particular soil, then we have to use the uh, intersection of the two vector layers. right? Which of the following function in GIS can be useful for identifying the places close to a mine that is getting affected due to mining activity? So this will be buffer. So our mine, it will be the area of mine will be a polygon, will be represented by a polygon, and then suppose some 10 kilometer of area close to the mine gets affected, then we can just generate a buffer polygon around that, and then we can mark that buffer area. Which of the following spatial function can be used to obtain the following output? So uh, these uh, these two different polygon layers, and then this is the output layer, so this will be a union overlay. 6th B, 18th B, 19th, 19th. Any other answer? 19C. Right. So we'll see. TIN is not useful in digital elevation models. So this is false. We saw that TIN can be used to represent the topography digitally very efficiently. Then we have which unique technique can be best used for making a thematic map with following information. Then we have temperature image, elevation image, roads layer, and city or town location layer. So here, this is a raster image, right? Elevation image is also a raster image. Then, or it can be a TIN image. Then we have roads layer. So roads layer in a small scale map, it will be like it will be a linear feature, right? And this is a city or town location layer. So this will be a point feature. So we have one background map with elevation image, right? So here it will be made of small pixels, uh, uh, and then each pixel will have a different value. So here a spatial overlay we can't use, because in spatial overlay we are simply doing operations between different layers which are intersecting. So here, and this was all the vector layers. So here we can't use spatial overlay, or interpolation also we can't use to show all these images together. Like the objective of interpolation is simply to find the value of some unknown points based on some sampled locations, right? So here we can topology also we can do. So here we have to do integration of raster and vector data. So this is a different type of raster and vector data. So if we want to show all this together, then we have to overlay the raster data first, and then on top of this we can show uh, the different linear features or different roads like this, and then uh, different point locations can be shown on top of this. So these all these different raster and vector layers, they have to be shown together. So this will be integration of the raster and vector data, and this is also known as the nearest neighbor technique. So this is Thyssen polygon. We just saw this. All right, so next we have maps. So a map is a two-dimensional representation of the whole or part of a three-dimensional earth surface on a flat surface with the help of signs and symbols. And then maps are the models of reality representing spatial relationships among real and abstract geographical phenomena. So in maps, it's like a 2D representation of uh, 3D features on a like on the surface of Earth. So Earth is a three-dimensional surface, right? With all the latitudes and longitudes. So we represent this on a 2D map using different signs and symbols. So a map will have so the geographic location has to be properly represented, right? So it will have uh, coordinates marked for proper representation of the location. So this location, it can be this location will be represented as, sorry, so here uh, yeah. So this each point will have an x and y value associated with it. So each point has to have a coordinate, and then there should be a direction, like there should be a north arrow in the map. Then there should be a scale, like we saw scales in some of the previous sessions, right? So there has to be a scale, like 1 centimeter on the map is like corresponds to how many centimeters in real life on ground, etc. So we need to have all this information in a proper map. So we are so there can be different types of maps, like large scale maps or small scale maps. A map that depicts small territories in great detail are large scale maps, and maps depicting larger areas are called small scale maps. So here, this is a small scale map. So here we can look at a larger area, but then in very small details. Whereas in a large scale map, it's so this large scale map is showing this area of Chicago. So this very small area, we can look at this in very much detail. So these river features and all, which are not visible in this small scale map, are we are able to see those in this large scale map. So it allows us to look at features in more details. Then we have coordinate system, right? So coordinate system is a reference system that uses coordinates or a set of values that show exact position of an object along and up or down the defined origin to define a unique position of an object on the earth's surface. So there are common types of coordinate systems used in GIS, like two-dimensional coordinate system, where location of a point is given by coordinates that represent the point's distance from two perpendicular points intersecting at the origin. So if this is the origin, then in a 2D system, the coordinates will be given by, so we all know this. So there are four subcategories of 2D coordinate system, like a plane Cartesian system, or there can be a polar coordinate system where the distance is given by r and theta. Then there can be a, uh, raster grid coordinate system where this is given by easting and northing the coordinates, or a map projection coordinate system. And then second, we have a three-dimensional coordinate system. So in a 3D coordinate system, the location of a point is given by three real values that represent the point's distance from a perpendicular projections on fixed perpendicular lines called axis intersecting at the origin. Right, it can be x, y, z, or it can be r, theta, phi. So r will be the distance of the radius, and then theta and phi will be these angles. Mm, yeah, the common three-dimensional coordinate systems used in GIS are as follows. So there is a three-dimensional Cartesian coordinate system, or there is a geographical coordinate system which has latitudes and longitudes. All right. So next we have map projections. So why do we need different sets of projections, right? So a globe is the best representation of Earth's surface with accurate location, shape, and proportions, but it may have size constraints. So this is a three-dimensional globe is the uh, it's like a representation of Earth's surface, right? But then yeah, so on this globe we can represent the location, shape, and proportion of different objects on Earth's surface. But then every time when we are representing a data, we cannot represent it in like three dimensions. We have to convert it to two dimensions and show, right? So if a so there are different types of projection to convert this three-dimensional data into two dimensions. So there are different mathematical operations which can be used to convert this 3D information into 2D. So if a globe is cut into pieces to make flat images, the shape and other information may get distorted. Hence, a map is required. So, if we look at this figure on the right hand side, so this is the Earth, and then it is reduced to it is reduced to the globe, which is a spherical surface. Now, here, uh, if we want to show this 3D globe into 2D, then um, just imagine that we are wrapping a paper around this globe, and then when we unwrap it and make it straight, then this 3D information becomes 2D. So this flattened globe, it can be represented as, so here we have different latitudes and longitudes, right? So when we make this into 2D, then the flattened globe, it will look like this. Right. So here, this each section is taken out like this, and then it is made into a flat surface. So it will look like this, the flattened globe. So this here, all of these angles together, they will converge at the polar region, right? So when we take it out, there is so much space towards the polar side, right? So when we join these, there are distortions towards the polar side when we represent it as a continuous map. So uh, when we are representing this data in a 2D map, then objects near the equatorial surface will be represented properly, but objects near the pole or countries which are present near the poles, they will be distorted, right? So, how to convert a three-dimensional spheroid with location information given in latitude and longitude values to a 2D flat map? So, this is what we discussed. So, the answer is map projection, right? So, map projection is a blended technique of mathematical transformation and geometrics to convert a 3D spheroid into a 2D flat map. Now, flattening a spheroid onto a flat surface, it always creates distortions to the actual spatial information regarding location. So, we talked about this that when we are converting 3D into 2D, there will be distortions in shape or size or directional relationships between different objects. So, like there will be distortions here. The objects in the polar region, they will look bigger than what they are depending on different types of projections that we are using. So we have to select an attribute which we want to preserve during the uh, conversion from 3D to 2D, because there is no ideal projection which will preserve all attributes like shape, size, and orientation. So we have to be selective based on the properties that we want to look at, and then based on this we can select the method of we can select different projection methods. So flattening a spheroid onto a flat surface always create distortions to the actual spatial information regarding location. So there are different criteria to classify this projection. So first is based on the spatial attributes like shape, size, and direction. So this is called basic type, and based on the techniques which are used to project the spheroid onto a flat surface. So we will look at these techniques in the next slides. So this is called basic techniques. So we have first we will look at basic types of projection which will allow us to preserve certain properties during this transformation. So first we have conformal projection. So this type of projection, it preserves the shape of small areas or angles for large areas. So during this transformation, we conformal, we preserve shapes or angles, shapes in small areas or angles in larger areas. In equal area projection, it preserves the area of the projected region. So it is often used for dot density maps and thematic maps. So for studies like if this is a reservoir, right? And then if someone is conducting a study on how the area of this reservoir changes with time. So in this case, when we are using the projection, we need the area of an object to be preserved during the transformation. Otherwise, the objective of the study will not be fulfilled, right? So uh, here we can use this equal area projection. So at time t1, if area reservoir area is a1, at time t2 it is a2, then using this projection we can conduct the studies of how reservoir area is changing and all, right? Then next we have equidistant projection, which preserves the distance between features on the projected region. So this can be used in studies where we are measuring the distance between two features, or there can be force projection called true direction, which preserves the direction between features. So depending on what is the application of your study, you can select each of these projections, right? So each of these properties, shape, size, and direction, is preserved one at the expense of others. So if I am preserving area, during my projection, then it is possible that the shape and direction, like other attributes, might be distorted. But then I will have to go with that type of projection because that is the objective of my study. So selection of a projection type depends on application, as there is no perfect projection that can preserve all the properties, right? Then we have some basic techniques of projection. So one type of projection was dependent on which property or which attribute that we need to preserve, right? Then there is second type of projection, which is dependent on the technique of how 3D data is being projected into 2D data. So the most common technique of projection is using a developing surface, right? Such as plane, cylinder, or a cone. A developing surface, it either touches or intersects the spheroid. So here what happens is, uh, so that we have three different types. There is planar, conical, or cylindrical type of projection. So here, um, this is my three-dimensional surface, right? And planar type of projection is taking uh, the projection of this 3D surface on a plane. So this plane will be tangent at any point to this spherical globe, and then you can imagine that there is a ball of like there is a light source inside this sphere, and it is projecting outwards. So if there is a light source inside, then how, and if we have drawn different lines on the surface of the sphere, then depending on where my planar surface is, these lines will appear differently on such surfaces. So here, if we imagine that there is a light source here inside, right? Then here, these lines of latitudes, they will appear as circles on a plane which is kept here. Then this second line, like this second line, it will appear like this. This third line, it will appear like this, right? So based on the position of this planar surface, the projection will appear differently in 2D. And then these are the lines of longitudes. So here, if the source is inside, light source is inside, then these will appear radially like this, right? Then, so depending on the positions of these surfaces, we have normal, transverse, and oblique type of projection. So in normal, this surface is uh, normal to the uh, poles. In transverse, it is tangential at the equator, and in oblique, it is at an angle. It is at a certain angle. So for normal, transverse, and oblique, we will get such different projections of these latitudes and longitudes. So these different types of transformations, we can select this based on the application. Like it will be based on the application of the user. So then next we have cylindrical projection system. So here we imagine that like there is a cylinder wrapped around this spherical surface, and the source of light is inside the sphere. And then when we project it on the 2D surface, then it will, all these lines, they will appear as straight lines here, right? And then when we unwrap this, it will appear like this. Right. So this is polar regions and this is equatorial regions. So in UTM projection, this type of cylindrical projection is used. So UTM is one of the most commonly used projections in GIS. So this is universal transverse Mercator. So in that, this globe is divided into different regions based like uh, so north and south, and each small region, it has an ID code associated with it. So if I want to represent a particular box, then it will be like it will be based on the uh, so here these are labeled as A, B, C, D, and so on. And here vertically you have different numbers, and then you have north or south. Then there is transverse projection for cylindrical, and there is oblique. So based on how this cylindrical surface is wrapped with respect to the globe, this transformation will be different. And then there is conical conical projection system. This is also normal, transverse, and oblique. So depending on their positions, we will have different types of uh, output geometries. Right. So you'll find these two questions very easy now. So please write the answers in the chat box. Yeah. So most of you got it right. Like all of you got it right. So for UTM, we just saw that it falls under cylindrical projection. And in a world map, as seen in Atlas, which country is most exaggerated? So we saw that the countries near the uh, polar region will be, so Atlas uses Lambertian azimuthal equal area projection. So in that projection, the countries near the polar regions, they will be more exaggerated. So Greenland will appear bigger than how it actually is. So the areas of this country will appear larger. So this is Greenland. That's it for this today's session. So this was the last interaction session for this course. Um, Please let me know if you have any queries, and all the best for your exam on 24th.
Ma'am, can we get the all slides in a PDF or PPT format?
Yeah, so if you go to your course, no, there you have this section for live interaction sessions. There you will find a Google Sheet attached. So there you have a folder which contains all of these presentations in that drive folder, and then there is links for all the video sessions also. So after this lecture, I will upload this PDF, and you can access it through the drive folder.
Okay, thank you, ma'am.
Okay. So thank you so much everyone for joining and actively participating. It was a really good experience for me also. So it was my first time being a TA for an NPTEL course. So it was a very good experience. And thank you so much for continuously joining through all the sessions and sitting there. So please let me know if you have any other questions, or we can stop the session here today.